Today we are going to see a small video which will present a demonstration of how a regular Markov chain always converges to the stationary distribution, irrespective of the starting distribution. This is something we proved in the last class. Today we will run a program where a transition matrix is specified. We will give different initial distributions and see that it always converges to the same distribution. So this is the program. I will share it on the website. You are encouraged to try it yourself, modify it, up to you. So let's go ahead. Let me run this program for you. So it says that our Markov chain has 3 states and we will go up to 15 time steps. The transition matrix is this. I have given it in terms of integers and then the program renormalizes it so that every row sums up to 1. Finally, this is my transition matrix. So let me start with the equiprobable distribution. So again, I am giving weights. The program will automatically normalize them to the correct probability distribution. So this is the probability distribution 1 by 3, 1 by 3, 1 by 3. So let's see what happens. It is not surprising that all 3 start at the same point because this was the case. But then finally you see that very soon in just 4 time steps, it comes to a stationary distribution. And this is something which you might remember, that the stationary distribution is around 0.36, 0.35, 0.34 for this. We will give many different probability distributions and see that it always converges to the same probability distribution. So let's try this with a different probability distribution. So last time it was equiprobable. Now let's say that we give very large probability to first 2 states and the last state has a very small probability, and let's see what happens. So you see that in the beginning 2 of the things are very close to 0.5, one is very small. Initially it goes through something, but finally it converges to the same distribution, which is around 0.36, 0.35, 0.34 or something, which should be the eigenvalue 1 eigenvector of this transition matrix. Okay, let me try one more. This time let's just give a huge weight to just one of states and rest will be small. And you see that once more the one state had a very high probability, but pretty soon it converges to a stationary distribution. So we gave different probability distributions and every time it converged to the same stationary distribution, which was not dependent on the initial distribution. Let's try it with a slightly different transition matrix. This time I will make it slightly more different. I will make the entries more interesting. And on one of the things, I will put a very huge weight. And let's see, so this is a new probability distribution. Run my program again. Change. The transition matrix has changed significantly. You see that the last entry at the bottom has become 0.98. So that means from the third row, you go to the first row. From the second row, also you go to the first row. So you keep going to the first row in some sense with high probability. Let me again start with equal distribution. And this time, the stationary distribution is going to be very different. The transition matrix is different, but then you kind of see that this is where the green line will always be very high and other 2 will be very small. Now I can change the probability distribution, but I will again go to the same stationary distribution. So I keep the transition matrix to be the same. Remember, the last entry is 0.98, and then let me give high weight to 2 entries and other 2, the other one is very small. And again, it starts in different positions, but finally it converges to the stationary distribution. This time the rate of convergence is slightly slow as compared to the first example. You might have seen that the first time when all the entries were around the same, the stationary distribution was like this 0.36, 0.35, 0.34. Within 4 or 5 entries, it converged. Here, it is converging around 8. So, when it converges is a good question, and it depends on the matrix and its properties. This itself is studied a lot. Let's give one more try with another distribution, which is very, very skewed. And again, the idea is that ultimately it should converge to the same distribution. You see that the beginning is different than all these, but finally it converges to the same distribution, which is the stationary distribution of this transition matrix. If you remember, we said that stationary distribution exists for regular Markov chain, but not for all Markov chains. So let me just modify the matrix slightly and make it not a regular Markov chain. I will make this slightly different, a cyclic Markov chain, such that the first entry always goes to second, the second entry always goes to third, and the third entry always goes to the second. And now, since this is not a regular Markov chain, so you can see this transition matrix and you convince yourself that this was like this 0, 1, 1, 0 kind of a transition matrix, which was not regular. So in this case, the states should keep fluctuating. We should not end up in a regular Markov chain. So let's see. So I will start with a simple one. And now you see that none of the lines go to the same value. They keep fluctuating. It's like a sine curve or something. And they never become constant. I can try it with a very, very skewed distribution too. But you will see it's kind of the cyclic pattern because they keep rotating around. It's not a regular Markov chain, so we don't expect it to converge to a stationary distribution. Thank you.